On this page, we'll tell about a few cautions and conclusions from hypothesis tests. It's not uncommon to see debate over the conclusions and implications of statistical studies. When we read the summary of a statistical study, it is important to evaluate whether the conclusions are reasonable in light of the study design. Here are some examples of some common pitfalls in study design. First, the study makes an inference based on non-random data. If the data come from a sample that is not randomly selected or from groups that are not randomly assigned, we should not use the data in inference procedures. Why? Because all inference procedures are based on probability. We can make probability statements only about random events. For this reason, we will build probability models from repeated random sampling or repeated random assignment. Without a random sample, we cannot use a hypothesis test to draw a conclusion about a population. Similarly, without random assignment of subjects to treatment, we cannot draw a conclusion about the relationship between two variables. Secondly, the study makes inappropriate cause and effect conclusions. We can make cause and effect conclusions only with data from a randomized comparative experiment. If data comes from a single observational study, we cannot make cause and effect conclusions. Third, the study overgeneralizes its conclusions. In the case of an experiment, if researchers randomly assign individuals to one of two treatments, statistically significant results suggest treatment is effective. This is an appropriate casual conclusion if the experiment is well designed. If the original group of individuals is not randomly selected, then we should be cautious about generalizing this conclusion to a broader population. For example, a well-designed experiment may provide evidence that aspirin lowers the incidence of heart attacks, but if the subjects are all white males, we cannot conclude that aspirin effects will hold for Black males or for women. In the case of an observational study, the sample must be randomly selected from the population of interest. So for example, if we want to draw a conclusion about teenagers nationwide, we cannot use a random sample of teenagers from our community, because teenagers from just one community don't represent the overall experience of teenagers nationwide or worldwide. The following graphic summarizes all these ideas. So the notice here, it says, how are individuals selected? Okay, either random selection, that's the good one, non-random. So anything in this is no good. That's why it's red. But the potentially, this blue row at the top could be good because it has random selection. But then you ask yourself, okay, within that, how are individuals assigned to groups? If it's random assignment, then that could be good. Non-random, not so good. So these are no good. So this is what we want here, this one square. Select a random sample from one population, randomly assign individuals in the sample to different treatment groups. That would be kind of the sweet spot, I guess. You want both of these things to happen. I want random selection and random assignment, both, if that makes sense. Okay. So now to summarize, if we want to draw a conclusion about a population, we have to have a random sample of individuals from that population. Also, if we want to draw a cause and effects conclusion about the relationship between two variables, we have to conduct an experiment that uses random assignment of individuals to treatments. In an experiment, if we have a random selection of individuals and random assignment of those individuals to treatments, then we can draw a cause and effect conclusion about the treatment, and we can generalize that conclusion to a broader population.